The Tonnenleger Bousard represents a remarkable example of late 19th to early 20th century maritime steam engineering, a period when robust mechanical reliability was essential for navigation safety. Designed as a buoy-laying vessel, Bousard was built to install, service, and recover navigation buoys that marked shipping channels, harbors, and hazardous waters. At the heart of this specialized working ship lies a powerful and elegantly engineered steam propulsion system, purpose-built for sustained low-speed torque and precise maneuverability. The steam engine aboard Bousard is a classic marine reciprocating steam engine, operating on pressurized steam generated by a coal-fired boiler. Water is heated in the boiler to produce saturated steam, which is then directed through control valves into the engine's cylinders. As the steam expands, it drives the pistons in a smooth, rhythmic motion, converting thermal energy into mechanical power. This reciprocating movement is transmitted via connecting rods and a crankshaft, ultimately turning the propeller shaft and driving the vessel through the water. What makes the Bousard's machinery especially fascinating in operation is its visibility and mechanical clarity. Unlike modern enclosed engines, nearly every moving component can be observed while running. The pistons, valve gear, flywheel, and lubrication system operate in full view, allowing engineers and spectators alike to witness the coordinated choreography of steam power. Each stroke of the piston is accompanied by the characteristic hiss of steam and the steady, authoritative cadence that defines classic steam propulsion. The engine is optimized for torque rather than speed, an essential requirement for a buoy layer. Handling heavy steel buoys, anchor chains, and lifting gear demands controlled power delivery and immediate response to throttle adjustments. The steam engine excels in this role, delivering strong pulling force even at very low revolutions. Direction changes are achieved through valve timing adjustments, allowing the propeller to reverse smoothly without the need for a mechanical gearbox, an advantage unique to steam propulsion. Supporting the engine is an extensive auxiliary system that includes feedwater pumps, condensate return lines, lubricators, and pressure regulation equipment. These systems ensure efficient operation and long service life. Lubrication is particularly critical, as oil must be carefully metered into the steam flow to protect cylinder walls and moving parts from wear. Engineers continuously monitor pressure gauges, water levels, and temperatures to maintain safe and stable operation. The boiler itself is a masterpiece of industrial craftsmanship. Constructed from riveted steel plates, it is designed to withstand high internal pressures while providing consistent steam production over long working shifts. Regular firing, ash removal, and water management are essential tasks, making the operation of Bousard a labor-intensive process requiring skill, experience, and constant attention. Beyond its technical significance, the Bousard stands as a living artifact of maritime history. In action, it demonstrates how steam power once formed the backbone of coastal infrastructure, ensuring safe navigation long before automated systems and diesel engines became standard. The deep mechanical sounds, The visible motion of steel components and the unmistakable presence of steam create an experience that is both educational and evocative. Today, when the Bousard steam engine runs, it does more than propel a vessel. It revives an era of engineering defined by durability, transparency, and mechanical honesty. The Demph machine in action is not merely machinery at work. It is a testament to the ingenuity and craftsmanship that shaped modern maritime technology. This beautiful 110-year-old Renault, brought to life by hand cranking, offers a vivid glimpse into the earliest era of automotive engineering. This 110-year-old Renault dates back to the pre-World War I era, around 1913 to 1915, a period when Renault was already a major innovator in European automotive engineering. The car is powered by a front-mounted inline four-cylinder gasoline engine, characterized by large displacement, low operating speed, and strong torque delivery, ideal for the rough road conditions of the early 20th century. The chassis is built from riveted steel rails combined with a wooden body frame clad in metal panels. Power is transmitted through a manual 3- or 4-speed gearbox to the rear wheels via a drive shaft, a relatively advanced solution compared to the chain drives still common in that era. Hand cranking the engine highlights the mechanical purity of the design. The fact that this Renault still starts and runs smoothly after more than a century demonstrates the robust engineering, precision machining, and durability that defined early Renault automobiles. The tractor-pulling made 2012 to 4.5-ton heavy modified Eurocup event represents one of the most extreme and technically sophisticated forms of motorsport in Europe. Hosted at the well-known Made pulling track in the Netherlands, this competition brought together elite teams from across the continent to compete in the heavy modified 4.5-ton class, widely regarded as the pinnacle of tractor-pulling engineering. In this class, vehicles are limited by weight rather than power, which results in astonishing technical solutions. Each tractor is restricted to 500 kilograms, yet power outputs regularly exceed 6,000 to 8,000 horsepower. This is achieved through the use of multiple engines, often 4 to 7 version 8 aircraft, automotive, or turbine engines mounted on a single chassis. Popular engine choices include Allison aircraft engines, supercharged automotive version 8s, and even helicopter-derived gas turbines, all synchronized to deliver maximum torque to the rear axle. The Made 2012 track was carefully prepared with layered clay and controlled moisture content to ensure consistent traction. This is critical as the pulling sled progressively increases resistance over the 100-meter track. As the sled's weight box moves forward, downforce on the sled pan increases dramatically, demanding precise throttle control chassis balance, and drivetrain durability. A single mistake in power delivery or weight transfer can instantly end a run. From a technical standpoint, the heavy modified tractors on display showcased cutting-edge drivetrain design. Custom-built planetary gearboxes, reinforced clutch packs, and billet steel rear axles are engineered to withstand immense torsional loads. Tire technology also plays a decisive role. Oversized pulling tires with hand-cut tread patterns are optimized for the specific soil conditions it made, allowing teams to fine-tune bite versus slip. Chassis design is another defining feature. Despite the visual chaos of exposed engines and superchargers, these machines follow strict safety regulations. Tubular chromoly frames, roll cages, engine containment blankets, and multiple kill switches are mandatory. At May 2012, safety crews and technical inspectors worked continuously to ensure compliance, underscoring how professional and regulated modern European tractor pulling has become. The Eurocup series adds an extra layer of prestige. Points accumulated at events like May determine overall championship standings, so teams arrive with meticulously prepared machines and well-rehearsed crews. Engine synchronization, fuel mixture calibration, and boost pressure management are refined through data logging and experience, often adjusted run by run as track conditions evolve. Spectators at May 2012 witnessed not only raw power but also remarkable reliability. Many tractors completed full pulls with engines operating at extreme boost pressures and rotational speeds, producing deafening sound levels and visible exhaust flames. The combination of mechanical violence and precision control defines why the heavy modified class is considered the Formula 1 inch of tractor pulling. Ultimately, tractor pulling, May 2012, demonstrated the essence of the sport: engineering ingenuity, controlled brutality, and international competition at the highest level. The 4.5-ton heavy modified Eurocup class remains a benchmark for innovation, proving that when regulations are tight and ambition is high, the results can be nothing short of extraordinary. The Lindwood welding Dragster startup, running initially on methanol before switching to nitromethane, is one of those experiences that perfectly captures the raw soul of vintage drag racing. For anyone who has spent time around classic dragsters, funny cars, or nostalgia machines, the ritual is instantly recognizable, but it never loses its impact. The startup sequence itself is pure mechanical theater. The engine is first brought to life on methanol, a safer and more controllable fuel that allows oil pressure to stabilize, cylinder temperatures to rise evenly, and the supercharged V8 to settle into a steady rhythm. During these first moments, the crew listens carefully, reading the engine by sound and vibration. Every pulse through the headers tells a story. Then comes the moment everyone waits for, the switch to nitromethane. Instantly, the engine's character changes. Exhaust note sharpens, idle becomes violent, and the air fills with the unmistakable scent of nitro. Throttle response turns brutal, with explosive bursts of power that feel less like acceleration and more like controlled detonation. Even at low RPM, the engine radiates authority. What makes this Linwood machine especially compelling is the setting. This is not a crowded drag strip or Bonneville salt flats, but a backyard startup. Intimate, unfiltered, and intensely personal. It is a reminder that what seasoned fans may witness dozens of times can be a once-in-a-lifetime moment for others. There is something deeply satisfying about seeing a compact, purpose-built Nitro Dragster fired up simply for the joy of it. No race clock, no staging lights, just sound, fuel, fire, and passion. Few mechanical experiences are as honest, visceral, or unforgettable. On the 28th of November 2014, Duncan Pittaway achieved a historic milestone by starting one of the largest four-cylinder car engines ever built, the 1911 Fiat land speed record car. Silent for more than a century, the 28.4-liter engine finally ran again after a 12-year restoration effort. Producing 290 bhp at just 100 revolutions per minute and an immense 876 Newton-meters of torque, the car represents early extremes of automotive engineering. With hand-primed cylinders, battery ignition, and double-chain drive, the successful start stands as a remarkable tribute to perseverance and pre-war engineering ambition. At Dawn Patrol 2009, Tom Kozura's Gnome Omega rotary engine offered a rare and authentic glimpse into the earliest era of powered flight. This is not an exaggeration. Only 6 Gnome Omega engines are known to survive worldwide, and one of them was running right in front of the crowd. Seeing vintage aircraft is one thing. Hearing one powered by its original rotary engine is something entirely different. The sound, vibration, and rhythm complete the experience and allow a true appreciation of early aviation. Before startup, the engine is carefully primed. Fuel is manually injected into each cylinder, one at a time, ensuring the correct mixture for ignition. This process must be completed across the entire engine, requiring patience and precision. Once primed, the crew coordinates the hand-propping procedure. Clear verbal signals are exchanged, and one person physically turns the propeller, while another manages the ignition system. When everything is aligned, the engine catches and fires. The result is a sound few people alive have ever heard in person. It is the same mechanical voice that echoed across fields and fairgrounds in the early 1900s, when aviation exhibitions and barnstorming shows introduced flight to the public. In 1916, this would have been the sound greeting families arriving by Model T to witness the future taking shape. The Gnome Omega produces 50 horsepower and was designed in 1909, with this example manufactured in 1912. As a rotary engine, the entire cylinder assembly spins around a fixed crankshaft, creating unique gyroscopic forces and a distinctive exhaust note. Hearing one run today is not a reenactment, it is living mechanical history. The Shvetsov AS-862 is a legendary Soviet radial aircraft engine, and its first start is always an impressive mechanical event. This 9-cylinder, air-cooled radial engine displaces nearly 30 liters and produces around 1,000 horsepower, delivering strong torque at relatively low RPM. During initial startup, priming the cylinders, engaging the inertia starter, and carefully introducing fuel are critical steps. Once ignition occurs, the engine settles into its characteristic deep radial rumble, with visible exhaust pulses from each cylinder. Widely used on aircraft such as the Antonov An-2, the AS-62 is renowned for durability, simplicity, and reliable operation in extreme conditions. The Cummins 1,500 kilowatts standby diesel generator, 277 480ths of a volt, is a high-capacity power solution engineered for mission-critical standby and emergency applications. Designed to deliver reliable performance during utility outages, this generator set is powered by a robust Cummins high-horsepower diesel engine, optimized for rapid load acceptance and stable voltage output. Operating at 277 480ths volts, it is well suited for large commercial facilities, data centers, hospitals, industrial plants, and infrastructure projects. This system integrates advanced electronic controls for precise monitoring of voltage, frequency, fuel consumption, and engine health. Heavy-duty cooling, efficient fuel management, and durable construction ensure dependable operation under demanding conditions. With Cummins' proven engineering and global support network, the 1,500 kW standby generator provides long-term reliability, fast startup, and consistent power when it matters most. The Rolls-Royce Griffon V12 Mk58 is a pinnacle example of British aero engine engineering, delivering immense power through refined mechanical design and precise manufacturing. With a displacement of 36.7 liters, this liquid-cooled, supercharged V12 was developed to meet the escalating performance demands of late-war and post-war high-speed aircraft. At full power, the Griffon demonstrates exceptional torque output, rapid throttle response, and a distinctive, authoritative exhaust note that reflects its large bore and long-stroke architecture. The engine features a 60-degree V configuration, forged steel crankshaft, and 4 valves per cylinder, enabling efficient breathing at high boost pressures. A 2-stage, 2-speed supercharger compresses the intake charge, maintaining power at altitude and delivering strong acceleration across the operating range. Fuel is supplied via a pressure carburetor, ensuring consistent mixture control during aggressive maneuvers and high load conditions. Cooling is handled by a robust liquid system with optimized coolant flow paths, critical for managing thermal stress during sustained full-power operation. The Griffon Mk58 was commonly paired with contra-rotating propellers, a solution that absorbed the engine's high-power output while eliminating torque-induced handling issues. Internally, heavy-duty bearings, reinforced connecting rods, and precision-machined components ensure mechanical stability under extreme combustion pressures. At full power, the Griffon V12 is not merely loud or fast. It is mechanically commanding, delivering smooth, relentless output with remarkable reliability. This engine represents the culmination of piston engine aircraft development, where brute force, engineering discipline, and operational durability converge in one of Rolls-Royce's most formidable power plants. The Curtiss-Wright R1820 Cyclone comes to life with a commanding presence, showcasing the rugged engineering that made this 9-cylinder Radial a cornerstone of mid-20th century aviation. During this startup and power run, the engine benefits from a complete new set of 18 spark plugs, 2 per cylinder, ensuring reliable dual ignition and even combustion across all cylinders. Fresh oil and clean fuel allow the lubrication and fuel systems to operate exactly as designed, stabilizing oil pressure quickly and protecting the massive master and articulating rod assembly during initial rotation. The Curtiss-Wright R1820 Cyclone is a single-row, 9-cylinder, air-cooled radial engine, developed in the early 1930s as part of Curtiss-Wright's highly successful Cyclone family. With a displacement of 823 cubic inches, 29.9 liters, the engine was designed to deliver high power with exceptional durability, even under harsh operating conditions. Depending on the variant, output ranged from approximately 700 to over 200 horsepower, achieved through higher compression ratios, improved supercharging, and refined fuel metering. This power run highlights why the R1820 was trusted in aircraft such as the B-17, DC-3, and numerous military trainers. Its sound, performance, and mechanical reliability remain iconic, making every successful start a reminder of classic radial engine excellence. The Jacobs R755-9 comes to life for its first start fitted with a test club propeller, a critical step in verifying engine behavior before flight hardware is installed. As the Radial fires, oil can be seen exiting the exhaust stack, an expected and reassuring sign on an initial run, indicating proper lubrication circulation through the cylinders and valve train. A safety chain is secured to the airframe, a prudent precaution in case the test propeller generates more thrust than anticipated during startup or throttle changes. This setup allows controlled testing while minimizing risk. The L4MB designation highlights the dual ignition system, combining magneto and battery ignition to ensure reliable spark delivery during starting and operation. During the run, oil pressure is carefully monitored, confirming a healthy and stable reading of 80 psi, well within optimal limits for this engine. There is a routine but essential check, validating that bearings, oil pump, and internal galleries are performing correctly under load. With a smooth idle, even firing pulses, and solid oil pressure, this first start demonstrates that the Jacobs R755-9 is mechanically sound and ready for further testing. It is a textbook example of disciplined vintage radial engine commissioning, where observation, patience, and respect for the machinery define every step. Bill Richards brings the Rolls-Royce Griffon V12 to life at the Anson Engine Museum near Poynton, revealing both the raw power and the uncompromising engineering of this legendary aircraft engine. The Griffon Mk58 is a 36.7-liter, liquid-cooled V12 developed as the ultimate evolution of Rolls-Royce piston-aero engines, designed to deliver extreme output for late-war and post-war aircraft. In Mk58 form, it was capable of producing well over 2,000 horsepower, driving large contra-rotating propellers. During startup, the dramatic backfiring seen from the exhaust stacks is typical of high-compression, large displacement V12 aero engines when mixture and ignition timing are being stabilized. Twin magnetos, 4 valves per cylinder, and a high-flow supercharger demand precise synchronization, especially at low RPM. Once settled, the Griffin's massive crankshaft, forged connecting rods, and robust cooling system allow it to transition smoothly into a deep, thunderous idle. Even on a trailer, the engine demonstrates the mechanical authority that made the Griffin a cornerstone of Britain's high-performance aviation engineering. The first start of this Bristol Hercules 216 radial engine marks the revival of a remarkable piece of British aviation engineering, brought back to life after at least 25 years of silence. The Hercules was one of the most advanced air-cooled aircraft engines of its era, developed by the Bristol Aeroplane Company and widely used during and after the Second World War. Months of careful preparation preceded this moment, followed by several evenings of patient adjustments before the engine finally responded. The Bristol Hercules 216 is a 14-cylinder, two-row radial engine with a displacement of approximately 38.7 liters. It is distinguished by its sleeve valve design, a defining Bristol innovation that replaced conventional poppet valves. Each cylinder uses a rotating and oscillating sleeve to control intake and exhaust ports, allowing higher volumetric efficiency, improved airflow, and better reliability at high-power settings. This configuration also contributed to smoother operation and reduced valve train stress, though it required extremely precise machining and lubrication. Before the first start, extensive work was required to ensure the engine was mechanically safe. Fuel systems were flushed, oil galleries primed, and the sleeve valve lubrication system carefully checked to prevent dry running. Given the long period of inactivity, internal components such as bearings, sleeves, and pistons needed time to re-establish oil films and free movement. Ignition timing across the twin magneto system was verified cylinder by cylinder, a critical step on a large radial engine where uneven firing can quickly cause damage. Initial attempts focused on coaxing the engine into rotation and combustion rather than immediate sustained running. With each evening session, adjustments were made to fuel mixture, ignition timing, and oil pressure response. The first signs of life, intermittent firing and uneven combustion, indicated that fuel was reaching the cylinders and the sleeve valves were beginning to seal correctly. Gradually, the engine transitioned from hesitant coughs to consistent firing across all 14 cylinders. When the Hercules finally settled into a stable run, the characteristic deep, rhythmic exhaust note confirmed that the sleeve valve system was functioning as intended. Oil pressure stabilized, temperatures began to rise evenly, and the massive rotating assembly, crankshaft, master rod, and articulated connecting rods demonstrated the inherent balance for which the Hercules was known. Even at low RPM, the engine exhibited the smoothness that made it ideal for heavy bombers and transport aircraft. The Bristol Hercules 216 was originally rated at well over 700 horsepower in later variants, powering aircraft such as the Handley Page Halifax, Bristol Beaufighter, and various post-war transports. Seeing and hearing one run again after decades of inactivity is a testament to both the durability of its design and the meticulous preparation behind the restart. This first start is not just an engine run, but the successful reawakening of one of the most sophisticated radial aircraft engines ever built. The Detroit Diesel 20V149 initial startup marks the awakening of one of the most powerful high-speed diesel engines ever produced for industrial and military use. Featuring a massive V20 configuration with a 149 cubic inch displacement per cylinder, this two-stroke engine delivers exceptional power density and torque. During initial startup, pre-lubrication and careful system checks are critical to ensure proper oil circulation through the crankshaft, bearings, and blower assemblies before combustion begins. Once fuel is introduced and the engine fires, the synchronized operation of the roots blowers and turbochargers becomes evident, forcing air through the cylinders to support efficient scavenging and combustion. The engine settles into a deep, commanding idle, characterized by the distinctive exhaust note typical of large Detroit two-strokes. As temperatures and oil pressure stabilize, the 20V149 demonstrates its hallmark traits: mechanical precision, rapid throttle response, and immense rotational force, confirming its readiness for heavy-duty service. The Detroit Diesel 16V149 is one of the most powerful and iconic high-speed diesel engines ever produced by Detroit Diesel. Featuring a massive V16 configuration with a 149 cubic inch displacement per cylinder, this two-stroke engine delivers exceptional power output, often exceeding 2,000 horsepower in industrial and marine applications. Turbocharging and roots blowers ensure strong airflow and rapid throttle response. Known for its distinctive sound, the 16V149 was widely used in heavy-duty generators, large vessels, mining equipment, and military platforms. Its robust construction, high power-to-weight ratio, and reliability under continuous load made it a benchmark among large multi-cylinder diesel engines. From a technical perspective, the 1929 Sulzer engine is characterized by low-speed operation, large displacement cylinders, and a long-stroke design optimized for high torque rather than high RPM. It typically uses mechanical fuel injection, heavy flywheels for rotational stability, and a water-cooled system to manage thermal loads during continuous duty. The massive crankshaft, plain bearings, and thick cylinder walls were engineered to ensure durability, smooth running, and decades of reliable industrial service. The Liberty V12 is a 27-liter, water-cooled aircraft engine adapted here into a Rolls-Royce chassis. Featuring a 45-degree V configuration, overhead camshafts, and dual ignition, its first startup highlights smooth firing, massive low-speed torque, and robust early 20th century engineering. The MTUMB 838 CAM 500 is a high-performance German tank engine used in the Leopard 1 and Bergepanzer 2. It is a 10-cylinder, 4-stroke diesel with a mechanical supercharger. Designed for military reliability, it delivers strong torque, rapid throttle response, and dependable operation under extreme battlefield conditions. At the Gomanek Vintage Agricultural Threshing Demonstration, the all-gear plus broad T140 stands out as a centerpiece of traditional field power applications. These events bring together historic farming machinery and techniques to showcase how landscapes were worked before modern combines and automation dominated. Among the classic machines, the broad T140 represents a generation of robust agricultural implements designed around mechanical simplicity and durable performance. The T140 is part of a series of broad agricultural machines widely used in Europe for soil preparation, harvest support, and related field tasks. While specific technical data for the T140 at Gomanek aren't widely published, components associated with the broad T140 and its variants, including conveyors, threshing supports, and transport mechanisms, reflect the practical design philosophy of mid-20th century agricultural engineering: heavy-duty steel frames, simple mechanical drives, and field-serviceable parts. During the event, the T140 may be seen operating in tandem with other vintage tractors and threshing equipment to demonstrate processes such as mechanical threshing, where cereal or grain crops are separated from stalks and chaff. Demonstrators often harness the engine power of a tractor or stationary engine to drive belt lines and powered shafts that feed material through threshing drums and separation mechanisms, replicating harvest routines from earlier agricultural eras. Such demonstrations emphasize the mechanical linkages, belt drives, and power transfer techniques that predate modern hydraulics and electronics. The T140's design, like many broad machines, is characterized by track-driven or tractor-towed configurations, allowing the work to be shared between tractor engines and implement mechanisms. Auxiliary equipment, such as conveyor belts, shaker supports, and linkage kits, was manufactured to adapt a basic chassis to specific tasks, from crop pickup to threshing and material movement. At Gomanek, operators and enthusiasts not only run these machines but explain the hands-on procedures required: careful engine management, clutch control, belt tensioning, and precise material feeding rates. Vintage engines must be warmed up gradually, often on diesel or mixed fuel, and maintained manually throughout the demonstration. Beyond the mechanics, these gatherings preserve agricultural heritage. They illustrate how machines like the broad T140, with its durable bearings, gear drives, and simple serviceability, powered farm productivity for decades before the advent of modern tractors and onboard power units. Seeing and hearing such equipment in action provides a visceral sense of the technological evolution in fieldwork and threshing, connecting spectators with the engineering challenges and achievements of earlier farming generations. The Hornsby Mammoth Recreation Crawler Steam Tractor is a faithful working recreation inspired by the original Hornsby Mammoth, one of the earliest track steam tractors ever developed. Built to demonstrate the principles of continuous track propulsion, this crawler steam engine illustrates the technological transition from wheeled traction engines to tracked vehicles, a concept that later influenced military tanks and heavy construction machinery. The machine uses a steam boiler to power a reciprocating steam engine, transmitting torque through gearing to the crawler tracks, allowing superior traction on soft or uneven ground compared to wheeled tractors. This recreation preserves the original mechanical layout, low-speed, high-torque characteristics, and robust steel construction typical of early 20th century steam engineering. As a unique piece, it serves both as a functional locomotive, a vapore singolata, and as a historical engineering reference, showcasing the ingenuity and experimental spirit of early tracked steam machinery. A highly unusual Volkswagen Type 1 Beetle project is being prepared for the Bonneville Salt Flats, where speed and experimental builds are celebrated. In this custom build, the stock Beetle engine has been replaced with a Continental W679, a radial engine originally manufactured in 1941 for use in an M2 tank and aircraft applications. This 11-liter 7-cylinder radial produces around 220 horsepower and was repurposed for automotive testing by enthusiast Mike Niemans, who adapted the engine to run on propane for cleaner fuel delivery. Rather than driving through a standard transmission, the radial engine is fitted with a 4-foot diameter reverse pitch propeller, adapted from a wind generator, mounted where the rear bumper would normally be. The entire assembly relies on custom engineering, such as using a tank clutch hub for initial setup, and ballast in the front to balance the rear-mounted engine weight. This build blends historic military engine technology with an iconic civilian car, pushing creative engineering limits and attracting attention for its sheer audacity. The startup of the T-3485 tank showcases the raw character of its V2 diesel engine. After preheating and system checks, the engine comes to life with a deep, mechanical rumble. Thick exhaust clears as oil pressure stabilizes, highlighting the durability and simplicity of this iconic World War II power plant. A Russian V12 diesel tank engine represents one of the most robust and purpose-built power plants ever developed for armored combat vehicles. Designed to operate under extreme battlefield conditions, these engines prioritize torque, reliability, and compact packaging over fuel efficiency or refinement. A well-known example is the V2 family and its later derivatives, widely used in Soviet and Russian main battle tanks such as the T-34, T-5455, and subsequent armored platforms. Typically configured as a 60-degree V12, these engines use large displacement cylinders, low engine speeds, and high compression ratios to generate immense low-end torque. This torque is essential for moving heavy armored vehicles across rough terrain, mud, snow, and steep gradients. Most Russian V12 tank diesels are water-cooled, naturally aspirated or turbocharged, and designed to run on a variety of fuel qualities, reflecting military logistics requirements. Durability is a defining characteristic. The engine blocks and internal components are massively overbuilt, allowing continued operation despite shock loads, vibration, dust ingestion, and temperature extremes. Simplified mechanical fuel injection systems are favored for their reliability and ease of field maintenance. Many designs also support compressed air starting, ensuring reliable ignition even in cold environments where electric starters may struggle. From an engineering perspective, Russian V-12 tank engines are not refined machines, but highly effective tools. Their unmistakable sound, heavy vibration, and visible mechanical character reflect a design philosophy focused on survivability and raw mechanical strength. Decades after their introduction, many of these engines remain operational in museums, restoration projects, and historical demonstrations, standing as enduring examples of large-scale diesel engineering built for war. The Bentley-Packard startup showcases the dramatic awakening of a massive 42-liter Packard V12 aircraft engine. As ignition begins, the engine transitions from deep mechanical inertia to smooth, authoritative operation. The distinctive exhaust note, heavy vibration, and sheer scale highlight classic aero engine engineering and exceptional mechanical presence. The Wright R3350 TC-18 is a large, air-cooled radial aircraft engine, and its first start is always an impressive technical event. With a total displacement of 54.9 liters and 18 cylinders arranged in 2 radial rows, this engine was designed to deliver up to 400 horsepower for long-range commercial aviation. The TC-18 variant is notable for its turbo-compound system, which uses exhaust-driven power recovery turbines to convert waste exhaust energy into additional shaft power, significantly improving fuel efficiency and overall performance. Fuel injection replaces carburetors, allowing more precise fuel metering, improved throttle response, and better operation at varying altitudes. Originally installed as an inboard engine on the Douglas DC-7C, the R3350 played a key role in the final generation of piston-powered airliners. During startup, careful oil circulation, ignition timing, and temperature control are critical due to the engine's complexity and massive internal loads, highlighting the advanced engineering of late piston-era aircraft power plants. The Bugatti Type 35B chassis XG9569 represents one of the most refined evolutions of Ettore Bugatti's legendary Grand Prix lineage. Introduced in 1927, the Type 35B featured a 2.3-liter supercharged inline-8 engine, producing around 135 horsepower, a significant increase over earlier naturally aspirated versions. This added performance made it highly competitive in major European races. Like all Type 35 variants, it employed a lightweight chassis, hollow front axle, and the iconic cast aluminum wheels with integrated brake drums. Chassis XG9569 is particularly rare, exemplifying Bugatti's unmatched blend of engineering precision, elegance, and motorsport dominance during the golden age of Grand Prix racing. The 4x4 Schachtermann off-road vehicle is shown tackling a severely slippery access road inside the Tayseng quarry, where loose gravel, wet clay, and embedded rocks combine to create extremely challenging traction conditions. The terrain is uneven and rutted, with sharp stones and patches of deep mud that place heavy demands on both the drivetrain and the driver's skill. At one critical point, the vehicle becomes partially bogged down as the rear wheels lose grip in a muddy depression. A man steps in with a shovel, manually clearing mud and compacted debris from around the tires in an effort to restore traction. This hands-on intervention highlights the reality of quarry work, where recovery often relies on practical problem-solving rather than specialized equipment. As power is applied, smoke begins to rise from the spinning tires, indicating aggressive throttle input as the driver attempts to force the vehicle forward. The tire smoke reflects intense wheel slip caused by the slick surface, but it also demonstrates the Cummins' torque delivery and the robustness of its 4x4 system. The drivetrain continues to push power to the wheels despite the hostile ground conditions. The rocky, gravel-strewn road emphasizes the harsh operating environment typical of quarry sites. Such terrain tests suspension articulation, ground clearance, and differential performance, especially when combined with mud and moisture. Every meter gained requires careful balance between throttle control and traction management. Overall, this scene captures the raw reality of off-road operation in industrial environments. The Cummins improves its durability and mechanical resilience, while the combined effort of machine and manpower underscores the demanding nature of off-road work in slippery, unforgiving quarry conditions.